What's up, Thermo Buddies? It's a good day to learn.
And be amazed.
Hi there, it's Ray.
And Jen.
Welcome to the world of thermodynamics.
Come and join us as we discover more about heat engines.
Let's go!
Heat engine and thermodynamics.
According to the first law of thermodynamics, heat and work are mutually interchangeable. This law does not mention above the direction flow of heat. The second law of thermodynamics gives the direction of law of heat energy. Before stating the law, let us see how heat energy is converted into mechanical energy in a heat engine. Heat engine is a device used for converting heat energy constantly into mechanical work. The schematic diagram of heat engine is shown here. The three essential parts of the heat engine are source or hot body, working substance, and sink or cold body. The working substance is taking a longer cycle of operation. In this process, the working substance absorbs heat from the source, transforms part of it into mechanical energy, and the remaining part of the heat is rejected to the sink. After completing the operation, the working substance comes back from its original state.
Heat energy is never converted completely into mechanical energy. That is, the efficiency of heat engine is never equal to 100%. Thus, we can define efficiency of the engine as the ratio of external work done to the amount of heat absorbed to the source. In heat engine, the working substance takes heat Q1 from the source at temperature T1, rejects the heat Q2 to the sink at temperature T2, and does some work W. Eta is equal to Q1 minus Q2 by Q1. Eta is equal to 1 minus Q2 by Q1. There are two types of heat engine, namely internal combustion engine and external combustion engine. Petrol engine and diesel engine are examples of internal combustion engine. Steam engine is an example of external combustion engine.
For better understanding of this topic, allow me to give another common example of heat engine which paved way to industrial innovation and development, the steam engine. Let's all watch and learn from this video.
Over the course of human existence, the most significant catalyst for growth has been our ability to draw energy from our world. Taming fire gave birth to the modern human, and drawing power from the wind allowed early explorers to travel the world. But today, we're going to explore the history and science behind one of humanity's greatest inventions, the steam engine. The evolution of the steam engine completely revolutionized our society. It opened new avenues for trade and caused mass migrations of rural populations into the newly industrialized cities. What I found most fascinating, talk about how it works. The engine takes energy stored in coal and converts it to heat. That heat is used to form steam, which expands into a piston cylinder, causing the pressure to increase and forcing the piston to rise against atmospheric pressure. No mechanical work occurs on the stroke because this chain can only transmit force in tension. The power stroke occurs when cold water is sprayed into the cylinder. This lowers the temperature, causing the pressure to drop. Atmospheric pressure now pushes the piston back down. We want to be able to quantify how much work is being done per cycle of this engine. To do that, we plot the pressure and volume inside the piston cylinder for one cycle, like this. The area inside is the work done, but this is the idealized PV diagram. In practice, there is a lot more energy being wasted. We lose a big chunk here because the steam is prevented from expanding to its full volume. A lot of energy is lost to the environment too. This is clearly visible with thermal imaging. The effect is made worse by cooling the entire cylinder with cold water. So an immediate improvement is to make a separate condenser. Here the steam can be cooled without cooling the entire cylinder. There are a lot more inefficiencies involved that reduce the total work done. Many of them are unavoidable, but we can improve the situation by upgrading the piston cylinder. The manufacturing techniques needed to bore accurate and strong piston cylinders were not available in the early days of the steam engine. That changed when John Wilkinson invented this machine. This boring machine allowed for precise machining of solid iron cylinders, which reduced steam leakage and made the piston cylinder stronger, thus allowing the max pressure to rise. We are starting to see a steam engine capable of sparking an industrial revolution, but this reciprocating motion isn't much use for most applications, especially with this flexible chain connecting them. What we need is rotational motion, which requires a different setup. To convert this linear motion to rotational motion, we need a crankshaft and connecting rod. We have turned this piston cylinder on its side, so atmospheric pressure can no longer force the piston back down, so we need to use steam on the return stroke. This requires a control valve to control when the steam enters and leaves each side of the cylinder. The valve is controlled by a cam. The steam engine is now working on both strokes of the engine, improving its efficiency and power, but piston engines like this do not produce constant torque. They'll pulsate in speed and torque during a single cycle, like this. This can cause vibrations and jerky movement. We can reduce this with the use of a flywheel, which stores rotational energy with inertia and evens the torque out. It's essentially a mechanical battery. David Robert demonstrates this beautifully with the V8 solenoid engine of his own creation. Here you can see the engine will continue to rotate without additional power, but the engine comes to a dead stop without a flywheel attached. The development of steam engines taught us a lot about thermal and mechanical efficiencies, and you may think that steam engines have become obsolete, but nearly all of our large power stations still use steam technology to convert heat energy, whether that be from coal, nuclear or solar, to mechanical energy. The technology has simply evolved into an even more efficient form, with steam turbines.
The fact that heat energy is never completely converted to mechanical energy has become the second law of thermodynamics. There are several equivalent statements of the second law of thermodynamics. Lord Kelvin stated that it is impossible to construct a device operating in a cycle for the sole purpose of extracting heat from a reservoir and changing it entirely into an equal amount of work without rejecting a part of the heat. This statement simply means an engine can convert only a part of the heat energy into mechanical work. Clausius stated that it is not possible for a self-acting machine unaided by any external agency to transfer heat from a body of lower temperature to another body at high temperature. This statement also means no heat engine is 100% efficient.